Okay, should I start now?
Yes.
Okay. Hello, everyone. Thank you for attending the defense of my dissertation, supervised by Doctors Claudia Prezzi, Manfred Strecker, and Magdalena Scheck-Benderoth, entitled The Thermal and Rheological State of the Central Andes and its Relationship to Active Deformation Processes. So the structure of the presentation consists of a brief introduction to the general characteristics of the region, leading to the open research questions, then a brief overview of the general workflow, a description of the different models that I constructed and their insights into the thermal and rheological state of the Central Andes, and an integrative analysis of the thermal rheological state and the observed active deformation processes. And finally, I'll give you some conclusions. Let's start then with the introduction. The Central Andes are part of a large orogenic belt located in the western margin of South America, where the Nazca Plate subducts beneath the South American Plate. And after a period of terrain accretion during the Neoproterozoic Cambrian, the region has been subjected to a series of subduction cycles with alternating periods of extension and compression. The main tectonic events that have shaped the present-day configuration of the Andes are the Famatingan orogeny in the early Paleozoic, which is characterized by extensive felsic magmatism and regional metamorphism. Then the onset of the Andean cycle in the early Jurassic, accompanied by widespread extrusion of mafic magmatism and extension in the western region of the present-day Andes. Then the arc migrated towards east in the Cretaceous, and there was onset of compression in the west, coetaneous with the development of the intracontinental Salta Rift in the east. And finally, during the Miocene, there were the main compressive phases of the Andean orogeny and a major magmatic flare-up within the orogen interior. Based on the structure, stratigraphy, and structure of the region, it has been subdivided into several morphotectonic units. The Altiplano and the Puna constitute a high elevation plateau, which is surrounded by thick-skinned fallen thrust belts in the west and the east, corresponding to the Chilean Precordillera and Eastern Cordillera. Farther east, the foreland is actively deformed by three different systems. Thin-skinned fallen thrust belt in the north, corresponding to the Savandian ranges, and to the south, two broken fallen systems, corresponding to the inverted Cretaceous reef of the Santa Barbara system, and the fault-bonded basement blocks of the Pampean ranges. Towards the forearc, the coast exhibits a pronounced morphological elevation with mafic compositions. And the present-day volcanic arc is located along the Western Cordillera and exhibits a marked diversion towards the east of the Atacama Basin, which is a prominent feature of the Precordillera, exhibiting very high seismic velocities in the crust. Throughout the plateau, there are several felsic deposits widely distributed throughout the plateau with minor mafic effusions, and these are associated to low velocity anomalies of the crust, which are interpreted to represent mid-crustal magma bodies, the Altiplano Puna magmatic body and Southern Puna magmatic body. In this line, the heat flow measurements show that there are anomalously high values in the Southern Puna and the Western Cordillera compared to the forearc and foreland, suggesting lateral variations in the thermal field. Presently, the region exhibits compressive neotectonic activity along the margins of the orogen, particularly in the Pampean ranges, the Santa Barbara system, the Subandean ranges, Precordillera, and Western Cordillera. Within the origin, most of the deformation is focused on the southern Puna, and the seismicity is reduced both in number and magnitude. The deformation system is complex with coexistence of compression and extension, and this is thought to be related to the collapse of the orogen and the delamination of large crustal blocks. In the forearc, the coastal cordillera also exhibits coexistence of compression and extension, as shown by the focal mechanisms, and these are related to complex interactions at the subduction interface, since most of these events are located at this interface. With respect to the vertical distribution of seismicity, within the orogen, in the Puna, most of the events are located in the upper 15 kilometers. Moving to the east, in the deformed foreland, the Santa Barbara system exhibits deeper activity down to 30 kilometers, and the Pampean ranges exhibit the deepest intraplate earthquakes of the region down to 40 kilometers at the Moho. Generally, these heterogeneities in the depth of hypocenters and also the location of the deformation have been attributed to variations in the deep angle of the subducting plate or the presence of inherited structures within the basement. However, the relationship between the thermal and rheological state of the region and the active deformation processes had not been fully investigated. And in this line, one of the research questions addressed in the dissertation concerns whether if the regional variations in the structure, temperature, and rheology of the lithosphere exert any control on the observed active deformation processes. But before this question is answered, it is necessary to investigate how the lithospheric structure and composition shape the temperature and strength distribution in the region. To accomplish that, I constructed a 3D density model of the region constrained by geological and geophysical observations and the forward modeling of the Bouguer anomaly. In a second step, I calculated the conductive thermal field based on the density model and lithological constraints on thermal properties, also after the definition of boundary conditions. And finally, I modeled the distribution of strength on the basis of both density and thermal models, and considering again the lithology of the main units to define rock properties. Let's start now with the 3D density distribution of the central Landis. Based on several geophysical studies that are shown here by the different colors, I decided to divide the crust into 3 different main domains. These are Western, Central, and Eastern domain, which are characterized by high, low, and intermediate seismic velocities, respectively. Within the Central domain, 2 additional domains were delimited: the Atacama block, that exhibits, as I said before, high velocities within the crust and also low seismic attenuation, and then the Altiplano Puna magma body, Southern Puna magma body, which is characterized by low velocities and high attenuation. Based on a previous model and also on the geophysical studies, I decided to then divide these different 5 domains into upper, lower, and middle crust, and the density of each of those domains was assigned in accordance with the prevailing lithology and the P-wave velocity, using these empirical relations between P-wave and density. In the mantle, the densities were obtained through the conversion of shear wave velocities, and for that I used a Python tool that is based on a method to convert seismic velocities in general into densities and temperatures, considering the effects of anelasticity and anharmonicity. And in these maps, you can observe the density distribution in the mantle at 3 different depth levels, and there is a progressive increase of density with depth from 100 kilometers to 200 kilometers. And you can observe also that there's a high density anomaly in the west, which is consistent with the subduction of the Nazca plate. After the model was populated with densities, the topography was removed in order to forward model the Bouguer anomaly using the software IGMAS until the calculated anomaly fit the measured anomaly. The residual anomaly shows a mode at minus 5 milligals with a standard deviation of 22 milligals. And around 10% of the region exhibits anomalies larger than 30 milligauss, which is considered the uncertainty for the model region. Overall, these anomalies are of a short wavelength compared to the resolution of the model and can be associated with geological features of the crust. This indicates that the regional density configuration of the central Landis is well reproduced. Given the complex structure of the density model with lateral and vertical divisions, it is better to analyze the results in terms of the average density of the crystalline crust. And in this map, I show the integration of densities over depth, so that the average density. And there's a correlation between the distribution of average densities and the Phanerozoic evolution of the region. As for example, in the Western domain, there are high densities which are consistent with the magmatic activity and the mafic rocks extruded during the Jurassic. And also here in the Atacama block, high densities that could be related as well to extensive periods in the Jurassic and also to mafic activity from all subduction cycles. Within the central domain, the low densities are most likely due to crustal differentiation processes throughout the long-lived history of the formation of the region, starting in the early Paleozoic and presently active since the Cretaceous. Particularly the lower densities in the southern Puna compared to the Altiplano are consistent with the delamination of large crustal blocks in the Puna, the recent delamination, and in the Altiplano with the underthrusting of the Brazilian crust beneath the orogen. Altogether, the density distribution reflects compositional heterogeneities that are interpreted as caused by different tectonic histories. Moving on to the thermal state of the central Andes, the 3D steady-state conductive thermal field was calculated based on the assumption that conduction is the main mechanism of heat transportation in the lithosphere. And I used the numerical simulator golem to solve Fourier's law for steady-state conduction after defining thermal boundary conditions and thermal conductivity and radiogenic heat production for each of the model units. The model has more units. This is just to show an example. The thermal properties were assigned in accordance with the prevailing lithology of each of those units and were taken from published average values for common rock types. The annual mean surface temperature from global climatic models and the temperature distribution at 100 kilometers in the mantle were used as upper and lower boundary condition respectively. And the temperature at 100 kilometer depth was taken from the same conversion of shear wave velocities that in the previous section. These maps show the temperature distribution, the model temperature distribution at 3 different depth slices below the surface, which means that topographic effects can be ruled out from interpretations. And at all depths, the same general trend is observed with high temperatures in the central domain, low temperatures in the western domain, and intermediate temperatures in the eastern domain. Furthermore, there's a correlation or partial correlation between the highest model temperatures and the location of these mid-crustal magma valleys. Farther deep in the crust of the central domain, but already in the mantle of the western and eastern domains, the same trend is still observable, but the high temperature anomalies lose expression with depth, particularly in the south. The high model temperatures for the central domain, despite the low temperatures at the upper and lower boundary conditions for this domain, suggest that the crust exerts a first order control on the model thermal field, with high temperatures in the central domain where the crust is thick and radiogenic, and low temperatures in the surrounding domains where the crust is thinner and the values of radiogenic heat production, are lower. Heat flow measurements provide a base to sort of validate the model, but they should be taken carefully because of their large uncertainties and the influence of non-conductive processes. So this map shows the model heat flow together with measurements of heat flow, surface heat flow in the region in the same color scale, and the stars indicate those measurements that are out of scale for which the value is annotated. And as you can see, there's no consistency between the model and measure values, but the regional trends are well reproduced with high model and measure heat flow in the central domain in the origin and low heat flow in the coastal cordillera and the forearc, and intermediate heat flow in the foreland. These misfits or deviations from measurements could be explained by convective processes. For example, in the coastal cordillera and the foreland, the misfits could be related to the infiltration of meteoric water in the high elevations and groundwater flow towards depressions. And in the western cordillera and the southern Puna, the anomalously high heat flow values are actually reported for regions with hydrothermal systems and brines. So summing up, the model reproduces well the conductive thermal field, assuming misfits are due to the effects of convective processes. The model temperature distribution is principally controlled by the crust, and the predicted high temperatures in the plateau are consistent with the location of geophysical anomalies and are supporting the relevance of rheological heat for mid-crustal magma body generation. However, further models would be required to assess the effect of coupled fluid and heat transport in the shallow crust, and the contribution of rheological heat to the heat budget. The most important outcome to keep in mind for the following sections is that the model temperature distribution is principally controlled by the crust. And to address the rheological state of the lithosphere in the central Andes, the distribution of strength was a model based on the thermal and density models, considering brittle and ductile deformation mechanism. And at all depths in the model, both brittle and ductile strength were calculated, with the resulting strength at each point being defined by the lowest of the two, as shown here in the graphic, where ductile strength is lower than brittle strength. The rheological properties for the calculation of the ductile strength were taken from published laboratory experiments on common rock types and were assigned in accordance with the lithology of each of the units, and taking care that felsic units were always weaker than mafic units. Calculated strength were integrated over depth to produce maps of lithospheric and crustal strength, and the main pattern that you can observe in these maps is that the central domain, so the origin, exhibits a weak lithosphere and crust compared to the surrounding forearc and foreland region. And then also, if you look at the ratio between crustal and lithospheric strength, you can observe that most of the strength for the origin resides in the crust, and the contribution of the mantle increases towards the forearc and the foreland. Considering the temperature distribution in the input thermal model, it is clear that the distribution of strength is dominated by the temperature distribution, with weak domains correlating with regions with high temperatures and strong domains presenting low to intermediate temperatures. The Atacama block represents an exception with very high strength and an intermediate temperature, and this highlights the effect of rock composition, since this domain is composed mainly by mafic rocks, which are significantly stronger than felsic rocks. The vertical distribution of strength shows that there are variations in the stratification of the lithosphere. So in the Santa Barbara system and the Pampean range is within the deformed foreland. The type of lithosphere profile corresponds to a jelly sandwich, which is characterized by a strong upper crust and a strong mantle, and this is stronger, of course, compared to the weak mantle in the Puna and the Atacama block, where the mantle is ductile and is completely weak, and the strength resides only in the crust, as in the creme brulee type of lithosphere. This is consistent with the variations in the geothermal gradients, with high gradients in the Puna Plateau and the Atacama Block compared to the Pampean Ranges and the Santa Barbara system. And also the location of the model brittle ductile transitions varies with the thermal field, as these are deeper in the Santa Barbara system and the Pampean Ranges, and shallower in the hotter Puna Plateau. In addition to this rheological model, and in cooperation with Dr. Sylvia Liu, we ran a geodynamic model for intraplate compression of the orogen foreland system in order to evaluate its quasi-present date dynamic behavior. And for the initial configuration of this model, the geometries and densities were taken from the density model and the lithosphere asthenosphere boundary from a global model. The initial thermal structure was set out to be equivalent to the conductive thermal model and the same thermal properties and rheological properties as these static models were used. The distribution of the model second invariance of the deviatoric strain rate show that deformation of the shallow upper crust is mainly focused in the Savandian Ranges, Santa Barbara system, and Pampean Ranges, which is consistent with observations in the field. And it is interesting to note that these regions with high model strain rate are correlated, especially with regions with high model gradients of strength, suggesting that lateral heterogeneities or lateral strong contrast of strength could be favoring strain localization. Altogether, the results of this model suggest that the strength distribution is strongly controlled by the thermal field, that rock composition exerts a second-order control on strength, and that the rheological certification of the lithosphere and the depth of brittle ductile transitions are governed by the temperature distribution. The correlation between the high second invariance of the deviatoric strain rate and the horizontal gradient of model strength suggests that the heterogeneous nature of the Andean crust may favor strong strain localization. In order to analyze the relationship between the thermorheological state of the central Andes and the active deformation processes, the distribution of earthquakes and faults was compared against the model distribution of strength. And for that, I compiled surface traces of faults with proven neotectonic activity, shown in blue, and the epicenters of earthquakes, represented by these red circles. And there's again a special coincidence of these reported seismic events and active faults with the high gradients of the model strength. And these are well consistent in the background with the model high second invariance of the deviatoric strain rate. These observations support the hypothesis that the lateral contrast or heterogeneities of the crust may favor a strong localization of strain. And with respect to the distribution of seismicity and strength in depth, I found that there's a correlation within the range of uncertainties between the model brittle ductile transitions and the depth at which the frequency of hypocenters start to decrease, as observed in other regions. And this implies that several of the well-constrained hypocenters are located consistently below the model brittle ductile transitions. And in different settings, this has been attributed to the propagation of aftershocks in depth, but this is not the case for the used dataset, as indicated by the spatiotemporal relationship between hypocenters. Now, if the reactivation of basement structures is considered through a reduction of the friction coefficient from 0.75 to 0.2, then in the Puna Plateau and the Pampean Ranges, almost all of the events are located within the brittle field. However, in the Santa Barbara system, the consideration of the reactivation of the structures, in this case of the Cretaceous Alta Rift, is not sufficient to account for the observations. This map shows that most of the hypocenters in the region are located above the 600-degree isotherm, which represents the lower boundary for the brittle behavior of olivine. In this line, mafic heterogeneities within the crust could serve as asperities for the initiation of seismic slip. So if a diaphragm rheology is considered for the crust of the Santa Barbara system, then the brittle ductile transitions are located deeper in the crust. However, there are still hypocenters located within the ductile regime. And only when the reduction in friction associated to the reactivation of structures and the presence of mafic heterogeneities considered through a diaphragm rheology, all the earthquakes are located above brittle ductile transitions in the brittle field. This figure summarizes the main findings of the dissertation with elevated isotherms in the thick orogenic crust of the central domain, associated with a weak lithosphere compared to the colder regions of the forearc and the foreland. Also, most of the interplate deformation is located in the transition between weak and strong domains, with most of the hypocenters occurring above the 600-degree isotherm. Particularly in the Santa Barbara system, I found that the heterogeneities of the crust, mafic heterogeneities, and inherited structures are necessary to account for observations. To finalize the presentation, the main conclusions of the model are that the heterogeneous crustal density configuration is coherent with a Phanerozoic tectonic evolution of the region. Then the thickness and radiogenic heat production of the crust exerts a major control on the model temperature distribution, and at the same time, the model strength distribution is mainly governed by the thermal field and to a lesser extent by rock composition, indicating a first order control by the crust. The regions with high horizontal gradients of model strength coincide especially with high second invariance of the deviatoric strand rate, and also with the reported seismic events and neotectonic faults, indicating that the heterogeneous nature of the crust may have a strong influence on the localization of strain and shortening. And the reactivation of inherited structure, the presence of mafic crustal heterogeneities, or a combination of both, seems necessary to explain the observed deep seismicity throughout the different morphotectonic units. Altogether, the cumulative results of the models indicate that the knowledge of the crustal structure and composition are crucial to understand deformation patterns. Thank you for your attention. That's all for my side.